In this video, you'll learn about half and full wave rectifier circuits. An important application of diodes is in the design of rectifier circuits. A diode rectifier forms an essential building block of the DC power supplies required to power electronic equipment. Shown here is a typical DC power supply. The first block is the power transformer. The primary coil of the transformer is connected to the AC line supply voltage, which in North America is typically about 120 volts RMS in amplitude and 60 Hz in frequency. The secondary winding of the power transformer is connected to the diode rectifier. We'll look at a couple of simple diode rectifier circuits in this video that take a bipolar sinusoidal input and produce an output that's unipolar. That is, it takes an input that has no DC content and produces an output that has some DC content. But because of the pulsating nature of the rectifier circuit, its output has too much ripple to be used directly by most electronic equipment. So later, we'll follow the rectifier circuit with simple filters. This helps to reduce the ripple in the output considerably. Still, however, there's generally too much ripple at the output of the filter to be used directly by sensitive equipment. So very often, the filter would be followed by a voltage regulator. We can use a diode regulator here as well, or more commonly, we can use an integrated circuit regulator. You should already be familiar with the simple half-wave rectifier circuit shown here. It's called a half-wave rectifier because it only uses alternate half cycles of the sinusoid. Now, two things that are of particular interest when designing a half-wave rectifier circuit are the specifications on the diode, the peak reverse voltage it has to be able to handle without conducting, and the maximum forward current it has to be able to conduct without overheating. So we're going to calculate approximate values for these two specifications by using a constant forward voltage drop model. As such, we're going to consider the circuit's operation in two cases. One, where Vs, the voltage on the secondary winding of the power transformer, is greater than 0.7 volts, and two, when Vs is less than 0.7 volts. So in case one, Vs is sufficient to cause the diode D to conduct. In this circumstance, we can, using the constant forward voltage drop model, replace the diode with a constant 0.7 volt source. In doing so, we see that VO equals Vs minus 0.7 volts. However, since in case 1, Vs is always greater than 0.7, it means that we've still got a positive voltage at VO, and therefore a net current flowing with this polarity through the diode and down through resistor R. The diode current can therefore be calculated as VO over R, and knowing VO and the amplitude that appears in the secondary winding of the power transformer, we can find the peak forward current flowing through the diode. The second case of interest is case 2, where Vs is less than 0.7 volts. In this case, there's insufficient forward voltage appearing across the diode D to allow current to flow in the forward direction. Therefore, the diode's off using a constant forward voltage drop model, and we can therefore replace it with an open circuit. So in this circumstance, the voltage that appears at VO is simply 0 volts. Because there's an open circuit, there can be no current flowing here. And with no current flowing through the resistor R, we're going to see 0 volts across it. So we can think about the operation of the half-wave rectifier circuit in two parts. We can think about what happens when Vs is greater than 0.7 volts. And in that case, we saw that the output simply followed the input minus 0.7 volts. And we can think about it in case 2, where Vs is less than 0.7 volts. In that case, the diode's off and the output is simply 0. So the input-output relationship is therefore captured by this plot on the right. When the half-wave rectifier is connected to the secondary winding of a power transformer, we know that the input Vs will be sinusoidal as shown here. And again, we can think about its operation in two modes, depending on whether Vs is greater than 0.7, that is above the red dashed line. In that case, we'll be in situation 1, and the output will follow the input but shift it down by 0.7 volts. And that's what we see, in this plot, where the black solid line is the input voltage Vs. We see that on the top parts of the sinusoid. So here, and then again here. And within those time windows, we see that the output plotted in blue is following the input Vs, but shifted down by the diode voltage, which with a constant forward voltage drop model is equal to 0.7 volts. The other case of interest is when Vs is less than 0.7. That's whenever the black waveform is below the horizontal red dashed line. So the plot doesn't work out perfectly in my sketch here, but that situation persists in these time windows here. And then whenever that's the case, then we know that Vout is equal exactly to 0. And we see the blue plot is just flat-lined at 0 volts during those time intervals. So in summary, we can see the half-wave rectifier essentially reproduces the positive half cycles of the input at the output, but then just has 0 output during the negative half cycles. That's why it's called a half-wave rectifier. Now, it seems a shame to, in a sense, waste the negative half cycles of the source voltage Vs. So to try to capture some of that, we developed a full wave rectifier circuit, which is pictured here. So in this case, the power transformer has a center tap, which is connected to ground on the secondary side of the winding in the rectifier circuit. So each half of the secondary winding produces its own source voltage Vs, and the polarity of Vs is indicated by the location of the dots in the secondary windings. And so that shows you that in the top half of the circuit, diode D1 is connected to the positive side of Vs, whereas in the bottom half of the schematic, we see that diode D2 is connected to the negative side of Vs. So that's the key point that's going to make this into a full wave rectifier. To understand its operation a little better, let's again consider what happens in a few different scenarios. First, when Vs is greater than 0.7 volts. Well, in that case, we've essentially got the same situation we had in the half-wave rectifier circuit. Vs connected through diode D1, which is now forward biased, and therefore using our constant forward voltage drop model can be replaced with a 0.7 volt drop, and then connected from there to the load R, across which we observe VO. So we know in this circumstance, VO is just equal to VS minus 0.7. Now what about the negative half circuit? Well, diode D2, there's D1 up here. Diode D2 sees the voltage negative Vs with respect to ground at the left terminal, and at the right terminal we've got the positive voltage VO. So clearly it's reverse biased and therefore may be replaced by an open circuit according to our piecewise linear model. So it's as if it's not even there. In this circumstance, there's a load current flowing through diode D1 and through the load R, and then back again through the top secondary winding. And there's no current at all flowing in the bottom winding because it encounters the diode D2, which is reverse biased. Now, second case of interest is what happens when Vs is, let's say, large and negative. A large negative, large in an absolute sense, but a negative voltage. So in this case, the situation is precisely reversed. Now, since Vs is large and negative, it's D1 that must be reverse biased. And so therefore we can model it with an open circuit and it'll have no current flowing in it. Whereas it's the diode D2 now exposed to a positive voltage because remember Vs is negative. So it will become forward biased and therefore exhibit a 0.7 volt forward drop across it. Here's D2, our model for D2. Okay. And so in this circumstance, currents flowing in the forward direction through D2, and then up here and down through the resistor, back again through the bottom half of the secondary winding. And there's no current at all flowing in the top half of the secondary winding. So what's interesting in this case is that, by the way, these diodes are cleverly connected in the full wave rectifier circuit. In both circumstances, case 1 and case 2, current flows through the load R in the same direction from top to bottom on these schematics, which means that in both cases, a positive voltage develops at VO defined with this polarity. In fact, if you follow the connections properly here, you'll see that VO is exactly negative Vs, which in case 2 is a positive voltage, a large positive voltage, minus again the 0.7 volt drop on diode D2 in this case. So even during the negative half cycle of the AC line voltage, you still get a positive voltage appearing at the output VO. There's a third case here, obviously, when Vs in an absolute sense is less than 0.7 volts. In this case, there's insufficient voltage on either of the secondary windings to get either of the diodes to turn on and conduct. So there's no current flowing anywhere in the secondary, and as a result, VO is 0. We can now plot the input-output relationship of the full wave rectifier in each of the 3 modes of operation we discussed. So the right side of this plot, we've got Vs greater than 0.7 volts. That's what we identified as case 1. And in this mode, the two are related by simple linear relationship where VO equals Vs minus 0.7. And therefore, we've got the slope of 1 here. The second case we identified was to the left of this dashed line, where Vs is less than negative 0.7 volts. We called this case 2, and we found that, again, we've got this linear relationship, except now VO is negative Vs minus 0.7 volts. So here we see the slope minus 1 in this part of the curve. Obviously, this is somewhat of an approximation. The whole piecewise linear, the whole constant voltage drop model is, of course, an approximation to the actual diode characteristic. Finally, we identified case 3 here in the middle for small absolute voltages Vs. And in that region, we see that VO equals 0 precisely. So the blue plot traces out the input-output relationship of the full-wave rectifier through all 3 modes of operation. And finally, we can think about what happens when the primary is activated with a sinusoidal voltage. That's Vs, shown in the black plot here on the right. And again, we can figure out what the output will be in each of the 3, under each of the 3 conditions we identified. So one is when Vs is, let's say, large and positive, large being larger than about 0.7 as shown here. So that was our case 1. It arises in this positive half cycle, and then again over here one more time over here in this plot. So in these time windows, right, remember that we've got the output voltage follows Vs shifted down by 0.7. The second case of interest is when the source voltage is less than negative 0.7 volts. So that would arise for the first time in this window here. So over here we're in case 2. And then again over here, whenever we've got the black plot of Vs below this line, we're in mode 2, and whenever we're in mode 2, VO is negative Vs minus 0.7 volts. Negative Vs is plotted on the same axis here as the faint dashed black sinusoidal voltage, and so that you can clearly see that during these time windows identified with the numeral 2, you see that the output voltage plotted in blue follows the input voltage, but again shifted down by 0.7 volts. And then finally, we've got these narrow windows of time in between here. There's one, here's another, right? Again here. In all these windows of time, we've got Vs less than 0.7 volts, and so we're in condition 3. So that's in here, again in here, and here, and so on. There's another one here, and here. So whenever we've got small voltages of Vs, the output voltage is at 0. So the end result is an output waveform plotted in blue here, where both the positive and negative half cycles appear at the output as positive half cycles, and with these narrow windows of time in between, where both diodes are off and there's no current flow in the resistor. You'll notice that there's never a negative voltage arising at the output VO. We've only got positive half cycles, and that's because the connection of both diodes D1 and D2 will not allow current to flow in the reverse direction through the resistor R. That then is the full wave rectifier.